all I've done relative to the first video on frequentist inference is erase the middle of the board and replace it with some language that is part of the lexicon of frequentist statistical inference. I've gone general on you, and so I have a new thing. I have a plan of why I have thetas. We'll call theta a population parameter that we wish to estimate using sample data and sample statistics formula. And we'll call theta hat an estimator using the language from last time. An estimator is a formula used to produce a statistic deployed on sample data, and then you wish to say what you get from this formula estimates some population parameter when you don't have all the data. You don't have the 13,000 observations. In your case, sadly, you only have 10. So theta hat could be x bar, and more formally, the formula for x bar. And theta could be mu x, the mean of x in the population. But it could be something else, and we're going to see that it relates to estimating variance from sample to population. And later on, see that we use the same language in estimating all kinds of things, using sample data and making inference to the population. So remember, theta is the population parameter of a statistic, any one. Theta hat is the estimator. It's the formula that you used on sample data to produce your estimate of what theta actually is. And I'm going to throw in at the end another one, theta tilde, and define theta tilde as an alternative estimator for theta. You could think of, in the context of the mean, you could think of the median, the normal curve, or it could be anything, doesn't matter. Another formula, an alternative idea. So instead of 1 over n times the sum of the xi, or alternatively the sum of the xi divided by n, which is small letter n, that is the estimator x bar. Let's try n minus 1. That could be theta tilde, an alternative way to do it. Frequentists have embraced this language as a mechanism for being able to say something about how good their estimates are, or alternatively, how bad they are. And I want you to know these definitions. I have them up here symbolically, and I'm going to explain them in the English language. This is a short video. It's just about this and nothing else. So, again, these terms, unbiasedness, consistency, and efficiency, and I'm defining that in relative terms. Unbiasedness, consistency, and efficiency are terms that frequentists use to refer to estimators. Estimators, formula for calculating statistics. So we have an estimator, theta hat. Theta hat is unbiased if its expected value, which you've now already learned and mastered completely, if its expected value is equal to the population parameter. If the average of your x bars taken 13,000 times turns out to be the correct answer, the population parameter, then that estimator is said to be unbiased. Note that there's no indication here that the size of the sample matters. This is a very important property. It's a very weak property in one sense, because a single draw at random from a population of 13,000 is unbiased. 10, also unbiased. It just means if we kept doing this over and over again, and this is the central idea to frequentist inference, if we kept drawing samples over and over and over and over again, and then we averaged the x bars from those samples, we would get the right answer. Such an estimator is said to be unbiased. This is for small samples. It's true in large samples too, but it's a small sample property. It doesn't matter how big n is. This one is large sample. Consistency. I've got people are going to be scared to death. This is lowercase letter n. It's the sample size. This is the sign for infinity. That's a little arrow. what I'm saying here is that n goes to infinity. Theta hat gets closer and closer and closer to theta. It did not ever get there. All we're saying here is that as you add data, you get closer to the correct answer. That is an estimator property, and it's one that is frequently used when samples are very large. It's essential, too. If you have an inconsistent estimator, think about this. If you have an inconsistent estimator, then you've got a piece of junk. Because if you can't say that as I continue to add data to the sample that I get closer and closer and closer to the correct answer, Houston, we have a problem. Efficiency, I'll speak of momentarily, but define it first in terms of relative efficiency. Recall I introduced my little character up here, theta tilde, and we'll call that an alternative way to estimate, let's say, the sample, estimate the population mean, theta tilde. Instead of dividing by n, small letter n for x bar, let's call x tilde a statistic aimed to estimate the population mean that we divide through, where we divide through by n minus 1, or anything. What we're saying here is that the variance of theta hat, when the variance of theta hat, let's call that x bar, actually let's write it in, is less than the variance of the alternative, let's call this x theta, the alternative way, then this one is said, theta hat is said to be more efficient than the other one. I'm going to erase the board and illustrate this in a moment, but the absolute efficiency of an estimator, I will add, is the case where the variance of theta hat is less than the variance of all other potential estimators of that population parameter. Now let's get a look before running away. Get a visual of what we mean by relative efficiency, and also at the same time by of unbiasedness. So what we're going to have here on the y-axis is simply the number of times. We're going to do this 13,000 times. The number of times that we observe a particular value for theta hat, or in this case x bar, and so this runs from our observed scores. You probably need to make an account. So let's say, like, what's the lowest score? Let's say the lowest score in the population on the test was about 30. Should be able to get that more or less by responding randomly. So we got 30. We know the high score is 100. We've actually observed one 100. Going to assume here it was the only one. We got lucky. What we're looking at here, though, here is the number of x bars. Number of x bars observed across 13,000 sample attempts with n equal to 10, small letter n equal to 10, and so we average up our 10s, throw them back, average again, we'll do that. So we're going to have 13,000 x bars, and let's say they're going to distribute it something like, they're going to be distributed normally. And let's make that 77 or so. Let's assume we got a good sample here, a really representative sample. You wouldn't with 10, as it turns out, or you wouldn't necessarily. Let's assume that we did. The expected value, you could see where the average is here. It might be a little off in my drawing. But remember that the expected value is simply the mean, and with expected value of the expected value of x bar is supposed to give you, if it's a definition of unbiasedness, it should give you the average in the population, and it would, right? Let's say that point is 77. That's how unbiasedness looks. That's how it looks. Now, suppose you had not observations of, well, there's other way to do it. And let's say you used n minus 1. That would turn out to be biased, but let's not focus on that. What if it were the case that simply by dividing through by n minus 1, using another estimator, that you got a distribution that looked like this? Which one of those would be better? It would be this one. This one would be said to be more efficient than this one because it has smaller variance. So let's say actually that this first one was theta tilde. Because we have so much data, 13,000, they're going to give pretty much exactly the same answer whether you divide by, so it's divided by 13,000 or divided by 13,000, 12,999. It's not going to make any difference in terms of the point. But what if it did this? What if it gave you one with less variance, an estimator with less variance? That estimator, the one with less variance, would be said to be relatively more efficient because it had smaller variance, a tighter distribution there around the true value. That's it for the lexicon. We're going to go and head toward the idea of taking X bars again as observations across repeated samples that actually never happen and standardizing them and produce a beautiful result coming up in Frequentist Inference 3.